5.6, number 335. 335. We have the integral natural log of cos x times tan x dx. All right, so it looks like a substitution is in order. It's extremely complicated. It looks like cos x has been put inside the natural log function, so my first suggestion, as always, would be to use that as the u substitution. So u equals cos x. Therefore, du equals negative sine x dx. All right. Now, if we replace cos with u, then I'll have ln u, and that's just fine, right? It's all in u. But I'll still have tan x dx. And down here, I've only got sine x dx. So let's look at this a little differently. Let me split up the tan into a sine on cos, because I do have, again, cos already as u. So it looks like we can fill in everything. Now, this may not be the most efficient way to do this problem. Looking at it here, I think I can think of a better way. But nevertheless, it's a good start, and it seems to be working. So I'll write this as sine x on cos x dx. Okay, so really everything can be filled in. Cos x here will give me ln u. Cos x here is u. Sin x dx is negative du. Right, I'll just transfer that to the other side. We'll have negative du equals sin x cos x. Or sorry, sin x dx. All right, so now we replace everything, and we get ln u, and cos x on the bottom is a u, and sin x dx is negative du. I'm just going to show it the outside already, instead of writing it in parentheses and then moving it out at the end. I'm pretty confident it's just going to slide out there anyway. But I still don't know the antiderivative of this automatically, so I need to make another u substitution. It looks like v should be ln of u. Now here there's no real composition to clue into. It's simply the fact that I know if I differentiate natural log, I'll get 1 on u. And I already see that sitting here as the other piece of this integrand. So it makes sense to choose v to be ln, thereby forcing dv to be 1 on u du, right, which works out perfectly. So now we have negative v, right? Natural log of u is v. The leftover 1 on u du is dv. So now we get negative a half v squared plus c. But v was really natural log of u, and u is really cos x. So therefore, transforming it all back into x values, we should have negative 1/2. Again, v was natural log of u, u was cos, so natural log of cos quantity squared plus c. Okay, so I was thinking as we were doing that perhaps there's a better way. So in this case, although it's not totally obvious, I could start the problem over to try a different way. It looks like it'll be a little more efficient. I'm going to do a double substitution there to finish the thing off. But here, if we had just let u be ln cos, it's hard to see this in advance a lot of times, but just to demonstrate here, u is ln cos, then du should be, according to the chain rule for natural log, is the derivative of the inside over the inside. Okay? But this is exactly negative tan x. So therefore that implies that negative du is tan x dx. So therefore everything can be replaced in one shot. Sorry about that. Everything can be replaced in one shot, and we'll have that the integral of u, that's the natural log of cos, right? That was the whole substitution there. And du is what? The negation of du is tan x dx, so tan x dx becomes negative du. Integrating will get 1/2 u squared plus c. But u was natural log of cos, and we come to the same conclusion in a slightly different way. And again, perhaps you might say slightly more efficient way. But it's not totally obvious that that would be the way to proceed from the beginning, especially since I've been stressing to always think about looking at the parentheses as a significant guide as to what substitution to make. But it's not always the case. You see here, it didn't have to be the parentheses. And over here, when we did the second substitution, there were no parentheses whatsoever to clue into. There's no substitution, no inner function, no composition that was totally obvious. And it was just the fact that the derivative of the one was the other that kind of led us as what the substitution should be.